one of the part of the partitions. Okay, and that's it. That is the partitioning theorem here. Okay. Right. Okay. So far we talk about the event or the outcome or the sample space. We haven't talked about the probability. So the definition one is about the probability. So probability functions is a function that is going to map from the sample space to 0-1 interval and assign a numerical value to a certain event, and we call it probability functions if it satisfies the following axiom here. So here we have 3 axioms. So the first one is that probability cannot be negative. Okay, so each of it I can assign a probability. For example, like take that graph as an example. So B1 could be, first of all, 0.2, 0.3, anything. Okay, and the only limitation is that it cannot be negative. Okay, and it can be 0 as well. It doesn't matter. And when you only consider within this sample space, and you want to know what is the probability that sample space happens, and that is 1, because we only consider in this sample space, right? So whenever a point or whenever an outcome is realized, then the sample space is realized, so the probability is 1. And then the third axiom is that if 2 events are disjoint, then the probability of that union is the addition of these 2 probabilities. Okay, so put it another way, we already know that from that graph, B1 and B2 are disjoint, right? So the probability of B1 and that is union, right? Union. Since they are disjoint, so you can directly add it up. Okay. Okay, so from that probability axiom, you can directly see the first bullet point below, right? So because we know that sample space is the union of a certain event with its complement set, right? And these 2 are disjoint. So since we know this is 1, and from your right hand side, we know that right? And that gives us the first bullet point. Okay. what else? Okay, and we talk about how to compute the union of two events if they are disjoint. But what if they have some overlap? Then you have to use this formula to calculate it. And actually, it's not that. It's quite intuitive. So it says that you have intersections, and this is A intersect B. Okay. So the way you just add up probability of A and probability of B, and minus the overlap part. The reason is that when you add up probability of A, then you kind of double count the intersection part for once. So you have to take that out, right? And since this part is since this part is greater or at least equals 0, and you can use this this property to conclude or to infer that this is actually smaller or at least equals the sum of these two, right? Okay, so just some basic calculation here. Continue. Right, then we talk about the join event. So here it's more like we only talk about one dimensions here, or if you have a very specific way to classify all the event, then you can put it in this graph. And we can also put it in a table, look like this one. So now we have two dimensions here. One is education label, okay, which is the row. No, it's actually the columns here. Okay, so C stands for the person you draw has the college degree. Okay, and N means that no college degrees. And then the other dimension is the hourly wage here. So H stands for a high hourly wage, which is $25 per hour. And L means that person receive a wage that below $25 per hour. Okay, and we can draw this table to kind of note the distribution of each subgroup. Okay, for example, like the 0.19 there represents the probability that says that now I randomly draw a person. The person has a college degree and at the same time earns a higher hourly wage. The probability will be 0.19. Okay. So etc. You can directly see the probability of a certain group directly from that table. And we can also add up. So for example, like here, 0.36. What does that mean? That means if I only care about the degree that person has, then I will immediately know that there are like 36% of chances that that person would have a college degree. Okay, no matter what kind of wage he earns. Okay, so that's how to read this graph, this table. All right, and of course, all the probability need to be added up at 1, right? That is the axiom. Okay, conditional probability. Okay, let's say that now that we have two event A and event B here within the same simple space. And if the probability of event B is greater than 0, the conditional probability of A given B already happens. We write it this way, which is P of A, and you put the vertical line there, and B. So the way to calculate it is put it this way. So first we look at the intersections, the event. Intersection of the event A and event B, what would be the probability of it to happen, and